Okay, hey, what's up, boys and girls? This is Boolean Noob. Here's with a comparator assignment. So we're gonna step through each part of the process. So here we have our first module, even two-bit parity with two inputs, A and B, and our output X. Essentially, what we're gonna do is going to do an XOR function against A and B, our two inputs, and we're going to output just an X with the XOR of A and B is gonna be our X output. That's this first module here. Okay, and then in the same module, we're going to write another module called even 8-bit parity. And all we're going to do is write four inputs, four XOR gates for A and B. So we're essentially going to have 8 inputs. And then we're also going to have two more inputs, two more inputs using the four outputs that we're going to get from these four. And we're going to do an XOR operation on those. And finally, we're going to get this output here, X. So if we're going to use runner schematic here, this is where schematic looks like. Let's expand everything here. Alright, and let's full screen this. Alright, so as you can see, we have two inputs here, two inputs here, two inputs here, and two inputs here. And all we really do is do an XOR function on each of these inputs. Okay, and we get this output X here. And each of those outputs is going to go into a different XOR function. You can see two more here, and then another two more outputs here, and that goes to our last XOR gate through here, and that's our output P. That's our schematic for this. Now, if we look at the test bench, because we want to see the simulation here, we have a test bench module, and we're going to have some regulators, and we're going to name it A, and we have a wire Y. So all we're going to do is import our even 8-bit parity module and map these modules with the simulation source. And we have here an integer I because we're going to use a for loop here, displaying every single one of the inputs. And here we also have a oh wait, not this. We don't need this delay here. But we're essentially going to go through each one of the uh, the 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 vectors here for 16 because 16 is a hexadecimal number. I don't really know why we need that, but oh well. And all we're going to do is map each integer to the input and display what its output is going to be based on calling this module, the 8-bit parity module. And we're going to store that into Y. It displays the bit number basically. And we're going to do that however many times we need to, so 16 times. And we're going to delay each time with a delay of 10 microseconds. And that's the end of our module. So if we run the simulation here, let's run the simulation. And let's put yes to that, and okay to that. Now we're going to be launching the simulation. Program is going to be executing the steps here. And now we see here our simulation. It's titled 5 because I've done this 5 times. Let's expand this. And let's make this as big as we can get. So let's see this a little bigger now. There we go. All right. So as you can see, each of these bits represents an 8-bit integer or number. Okay, and we do this for every single number that we need, and it's going to go for all 16 hexadecimal numbers: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, which would be A, 11, which would be B, 12 C, 13 D, 14 E, and 15 F. Total of 16 hexadecimal numbers. And each 8-bit integer is also going to be represented by its hexadecimal equivalent, depending on what the number is. So as you can see here, we have a value of 1 if it's on, value 0 if it's off. What is a 1? This is also 1. And we can play with this at will. If we want to make this 0, or if we want to make this 1, go back there. So basically, that is our timing bench, and you already saw our output as well. So that's essentially it. Alright guys, that was it for this comparator assignment. Have fun, like and subscribe. Take care. See you in the next one.